In this video, we're going to explore the product rule for differentiation. Assuming that both f and g are differentiable at the argument x, then the sum rule and the difference rule allow you to find the derivative of f plus g and f minus g very simply in terms of the derivatives of f and g individually. And the shorthand is the derivative of a sum is the sum of the derivative, and the derivative of a difference is the difference of the derivatives. The question here is, what would the product rule be? How do we find the derivative of the product of two functions? Now, of course, a naive guess is that the derivative of a product should be the product of the derivatives. And by the way, we already know that such a rule sort of works with products of limits. The limit of a product is the product of the limits. So it seems like a reasonable guess. So let's give this guess a test drive. We're going to find the derivative of x squared. And of course, this is a good test case because we already know what the answer should be. But we're going to rewrite x squared as the product of x times x. And now we're going to try our putative product rule. If this is really correct, then we find that the derivative of x squared should just be 1 times 1, which is the constant function 1. But we already know that the derivative of x squared is 2x. That's by the power rule. So 2x is not the same as the constant function 1. So there's no way this product rule, this guess, is correct. So we're going to have to work at this. We need to find the derivative of a product based on the definition of derivative. And so here it is. This is the limit of the secant slope we would need to calculate the derivative of the product. Now, if you're not sure about this, let's officially give the product function a name. Call it p of x. And if that symbol on the left is p of x, then of course here is what you get when you get p of x plus h. And if you evaluate p of x, then we indeed have the difference quotient p of x plus h minus p of x over h, and we're taking the limiting value as h goes to 0. So indeed, this should give us p prime of x. Now what we're going to do is we're going to set aside this expression and just concentrate on some algebraic manipulations on the difference quotient before we take the limit. Now, we claim that the top expression is the same as this second expression. What have we really done here? So here are two expressions, f of x plus h times g of x, and we have subtracted and added the same expression. So the net result, of course, is that we've added 0. And you can see that, yeah, this is going to give us the same thing. Now, why on earth would we be interested in doing such a thing? Well, we'll see that it simplifies some things down the road. Now, let's break apart this fraction across that sum. So we're going to have the sum of these two fractions. Now, we'll notice that we have like terms here and like terms here. So we could factor both of those out, and we'll get this expression. Now what we're going to do is we're going to set these two expressions off to the side and concentrate on each individually. So here's this right-hand term. And we're going to look at the limit of it as h goes to 0. Now, there's a product rule for limits, so we can take this product and take the limit of these two factors individually. And of course, g of x has nothing to do with h. It's constant with respect to h, so that limit is just going to be g of x. Now, the other limit you should recognize is the definition of derivative. So as we take h going to 0 in this case, we're going to recover f prime of x. So the limiting value of this expression turns out to be g of x times f prime of x. So we'll put that back into position, and now we'll concentrate on the other expression. Looks vaguely similar, but there's going to be a subtle difference in this. We'll use the product rule for limits again to break this apart. And now we see the definition of the derivative g prime of x here, so that is quite analogous. Now here we're running into a tiny little subtlety, and we want to recall that if f is differentiable at the argument x, then f must also be continuous at x. Now, what does this mean? The consequence is h goes to 0, certainly x plus h approaches x, and since f is continuous at x, it means that f of x plus h has a limiting value of f of x as h goes to 0. And so that limit is just f of x. So here, this other expression has limiting value f of x times g prime of x. So we're going to take these two results and we're going to transport them back into our big calculation. So where were we in that? We had the limiting value of this difference quotient, which we expanded by adding and subtracting like terms on the inside. We can split that across the sum, and the limiting value here of the sum is the sum of the limits. And we isolated each of these individually, and these are the results we came up with a moment ago. So this limiting value is f of x times g prime of x plus g of x times f prime of x. And there is our product rule. Now remember, we've assumed that f and g are both differentiable at x. That's required in the hypothesis of this theorem. So this is the product rule that we sought. And you'll notice that it is more complicated than the sum and difference rules. So let's go back to our silly example, derivative of x squared. We'll use the new and improved product rule that actually works. Derivative of x times x should be x times the derivative of x plus, flipping the roles, x times the derivative of x. And now we get x times 1 plus x times 1, and that's 2x, and that is indeed what we expected to find. Let's try a more complicated example. If we know that the derivative of sine is cosine and the derivative of x squared is 2x, then the product rule allows us to conclude that the derivative of the product, sine x times x squared, is going to be sine x times the derivative of x squared plus x squared times the derivative of sine x. Let's take a minute to explore the symmetry of the product rule. So what do I mean by this? Well, the function f of x times g of x is obviously the same as the function g of x times f of x because multiplication is commutative. These are clearly the same functions, so they should have the same derivatives. Now, when we apply the product rule in the first case, our template for the product rule gives us this expression. Of course, in the second function, we've just changed the role of f and g, so we could change the role of f and g here, and we better get the same thing. And indeed, we do get the same expression whether we use the template straight on the bottom line or you just switch the roles of f and g. So these things are equal no matter how you cut it. More generally, you should notice that because of the commutativity of both addition and multiplication, there are actually 8 different ways you could write out the product rule, and of course these are all equivalent. My suggestion is don't try to just pick out one that you always use. You want to somehow be flexible about it. So I would suggest a more abstract way of thinking about the product rule. When you have two gadgets that you're multiplying together and you want to find the derivative of the product, just remember that there are 4 basic players. They are the 2 original functions and their derivatives. And you got to mix these together somehow, and you have to take a pair of products. And how do those products look? Well, just remember to mix the derivative with the other one. As far as the order of where the multiplication and addition wind up, it really doesn't matter. So now let's look at the consistency of the product rule with the scalar multiple rule. So what I'm about to describe can cause some undue difficulty when beginning students of calculus are taking derivatives because they wind up doing more work than they need. So suppose k is a constant and f is differentiable at x. And we want the derivative of k times f of x. Now, a lot of students, when they see this expression, they need to take the derivative of the expression, they see a product and they think, well, let's use the product rule. Well, yes, you can obviously do that. K times the derivative of f plus f times the derivative of k. But the thing to notice is the derivative of a constant function with respect to the variable x is 0. So this whole term on the right vanishes and all you're left with is k times the derivative of f of x. What do we recover? We recover the scalar multiple rule. This is something we already knew before we learned the product rule. So what's the lesson? The lesson is when you see such a derivative, you might have an instinct to take the product rule, but you should think to yourself immediately, yes, I could do that, but that's just going to return me back to the scalar multiple rule. So you should use the scalar multiple rule fearlessly, even if the thought occurs that you should do the product rule. You should just remember that if you did the product rule, you just get back the same rule for the scalar multiple rule.